Good morning, everyone. Happy Wednesday. How's everybody doing today? Good. Had a good week? Good. Uh-oh. Why maybe? You have or you haven't. I'm not sure why maybe came in there. Uh-oh. A week is a good thing to be. Yes, that's a good start. Good. I'm sure some of you are still feeling effects from snow and ice. Some are um, probably not overly affected by it and everywhere in between. It's kind of the nature of large storms. Yeah, some of us are still getting winter weather. See, all the fun. There you go. Yeah, no, we got ice with a little sleet. So kind of a mixed bag from that perspective, but definitely not a ton of snow. We got some lake effect snow, but not a lot. So tiny little things to get us going in that perspective. But glad you're here either way. Glad you um, made it here. Glad you're here. So today we're going to talk a little bit about some of Newton's laws. We're going to extend some of the ideas we've been working on, practice on some new things. Not all of it will be new, but some of it will hopefully be a little bit new for you. We'll watch a video about um, understanding a little bit more, something we've talked about as well. Okay. We will have some time to do our force, mass, and acceleration lab discussion. If we do have time for you to complete it, you will be able to do that later in class. So if you don't have your materials with you right now, don't stress about that. Um, I'll give you time during break and put the list up again so that you can grab those things if you need them. The lab report is here in the classroom. It's also in our class page so that if you need to have that available for you to be able to see what we're doing, that's there as well. So let's go ahead. We're going to say our word of prayer before we get started into our conversation about physics. Dear Heavenly Father, I thank you so much for this day, God. I just thank you for the opportunity to come together, to continue to grow and learn, God, and just to spend time together. God, I thank you for the blessing that each of these students are in their household, in their peer group, in their co ops or youth groups or whatever it happens to be. God, I thank you for all the gifts that you have given these young people. And I just pray that you would give them space and opportunity to use those gifts to serve you. God, reveal to them the special things that you have for them. Let them know that they have a place in your plan, in your design that no one else can fill. God, I thank you for protection during the storm. There lots of people have been affected by it, but God, I just thank you that you have allowed us to be safe. You have allowed us to come back together and spend time together. God, we love you and we thank you. We ask all these things in your name today. Amen. All right, so let's get started with some of our things here. All right, so this time our brain stretches are going to be a little bit different. I'm going to put three words up here on the board, and your goal is to figure out what is alike, what bonds the three words together. Okay, just like before, I'm going to ask you to let everyone have an opportunity to look at the words, and then I will call on someone who has not gone yet to get an opportunity to share their idea first. Don't worry about the name that comes up. Remember, that's always the name from the previous week. Okay. But just remember that. Silas, people email me prayer requests when they have them. If you'd like to share one, you always can, or people will send them to me in a private chat, which is always welcome. Um, yep. I allow you guys to send them to me anytime you want, but a lot of people feel more comfortable just sending to me in a private chat. But when you mention anything in the pre-class time, I give you um, time to do that as well. So, and a lot of times I'll pray over you guys separately, not necessarily in class, like things that you send to me outside of class, but you're always welcome to share them. Okay, so our first set of words, again, make sure that you don't give any guesses until we've gotten to that point. Your first triplicate here: McDonald's, St. Louis, and a foot. So be patient, take a minute to think about them, let everyone have that same minute. I have paused chat so that there's no possibility that anything gets given away. You guys are not amazing at being able to just sit quietly and wait. A lot of us feel the need to be typing every second, which I get it, but I want to be fair to everyone. So everyone has an opportunity to try them first. So you're looking for what bonds the three words together. Do they have in common? Whatever it happens to be. Just a moment, I'll get our first guesser up here for you to see, and I'll turn chat back on during that time. Okay, Piper, as I resume chat, you get to type first. Everybody else has been on pause, but Piper, feel free. If you have a guess how these three words are related, you get to go first. After Piper guesses, then everyone else can guess. Okay, everybody put in a guess then. This is just a different type of puzzle, I guess, if we want to think about it that way. All right, I've got several of you who haven't yet put in a guess. So if you want to put a guess for this one, now is the time. Put a guess for what the relationship is between these three words before we move on. Get everybody to put in something, at least try. All right. The correct answer is they all have arches. So McDonald's is called the Golden Arches. St. Louis has the large. Yeah, so there you go. Now you're getting to see kind of the first try on these. Definitely a fun relationship. Okay, we've got another set. Here we go. Next set. What do you mean pretty vague? It's a relationship between those 3 words that's unique. Yeah, right? So part of this is you having to think about the relationship between the words. A lot of us get very focused on literal things or just our most quick answer instead of actually putting some real thought into it. Hence the idea of a brain stretch. It's supposed to force you to really look a little more deeply than just a simple quick response. It's going to force you to really think through the information. That's why it's a brain stretch. These are great for your brain. Yep. All right. Our next triple here, I'll pause chat because you guys can't help yourselves. Our next triple are going to be baseball games, trash dumps, and blue jeans. You're looking for the relationship between what they have in common, baseball games, a trash dump, and blue jeans. So I'll give you a moment to look with quiet chat. I think several of you have mentioned that it's helpful to have chat quiet during this time, just because so many people keep typing even when you're trying to think a little bit. So I don't mind doing that if it helps you have just a moment to think about it. All right, let's see who's going to get to guess first. All right, so let me turn chat back on. Sean, you get to guess first, and then everybody else can go after that. Go quick so everybody else gets a turn. Okay, everybody feel free to put a guess in there if you would. Please put your guess in there. Good. Lots of us kind of having some ideas. Not sure what genes have to do with some of our guesses, but that's okay. The trick for these is all of them have the same word that is associated with them, or they have the same part in common as far as a phrase. Doesn't have to mean the same thing in all of them. But that's someone asked, what are we trying to do? I don't understand what you're looking for. Looking for some relationship between these 3 words. What do you mean define a trash dump? You know what a trash dump is. Don't overthink that. You know what that is. There's no trick here. This isn't a trick, I swear. All right. Correct answer here. Silas, if you choose to do that, that's fine. That's not a problem. You don't need to, but if you choose to do that, that's fine. Okay. So the relationship for this one is that they all have flies. So think about that. In a baseball game, what is a fly? It's kind of thinking about it. What do we mean when we talk? Yeah, like a fly ball, right? There you go. A trash dump, like the insect, a fly. And then in blue jeans, another name. Yep, another name for a zipper is a fly. So there you go. That's how they're all related. Okay, we've got a couple more of these. Our next set of three that you're looking for a relationship is going to be a person, an artichoke, and a deck of cards. A person, an artichoke, and a deck of cards. So take a minute. We'll look at those and then we'll give an opportunity for someone to put a guess out there. Okay, good. So those are our three options: a person, an artichoke, and a deck of cards. All right, let's see who's going to make our next guess here. Okay, Paul, here in just a moment, I'll open it up for you to be able to make the first guess. Kind of fun. Okay, I'm going to unpause chat. Paul's going to be able to have the opportunity to guess first. And then once he has guessed, everyone else can guess as well. Give him an opportunity to guess first. All right, everybody go ahead, put in a guess if you would like to do that. Good. See, we're starting to get better at them. Very good. So the association is that they all have hearts, right? A person has a heart. An artichoke inner part is called an artichoke heart. And a deck of cards has a suit that is called hearts. So kind of a fun association. Hopefully that was easier, more fun, interesting. All right, we got one more set of these. Since it's our first time, I put an extra one up here. So here is our last one, which I will kind of fun for everybody, but here's our last one for this one. See? That's why you get a bonus one today because it's your first time when we're learning all about it. So for this one, the three words are a ball, a salad, and a coin. A ball, a salad, and a coin. So give you just a moment to think about it. All right, so let me unpause this. Actually, I'm going to choose the person first so they have an option to get typing if they'd like. All right, Jude, this one is for you if you would like to guess first. Jude can guess first, and then everyone else can guess after he has had an opportunity to guess. Okay. If Jude doesn't know for sure, you guys can guess now. What is the bond between these three words? So one of the things you'll notice about this, it rarely has anything to do with the actual word that you see on the screen. It's more about how they're related. So it helps when you're thinking about those. Yep, there we go. So good. Several of us are on the right track. That one was good. This one was they can all be tossed, right? You can toss a ball, you can toss a salad, you could toss a coin. Kind of a fun expression of all those. So I hope the brain stretches are interesting for you. I hope that you're enjoying all of them. Hope that it's something fun. He's just now come back, Sophia. All right. So let's circle back to the lab that we were talking about last week. Okay. When we were doing our lab with our static and kinetic friction, what did you notice about those two values, your static friction compared to your kinetic friction? What did you notice about those just in general for all of the objects you chose? What patterns did you notice? Okay. Everybody else, what did you notice about how the static and kinetic friction values compared to each other? Okay. So there we go. Now we're seeing some patterns. Kinetic friction value was always lower. Is that what a lot of you saw? Some of us had to do it several times. Yes, that's about right. Good. Yep. Static was higher. Kinetic was lower. Okay. Good. Okay. So then, second question before we talk about why some of these might be true. When did you notice that the static and kinetic friction values were really close? And when were they further apart? Not when you had to redo it, but just throughout the whole experiment. Did you notice a time when the values were closer together? There wasn't much difference between static and kinetic, or a time when the values were further apart? Okay. Okay. So this said when we changed um, into the rug or into the concrete, the values were further apart. Okay. What else? What else did you guys notice? Okay. Kept snacking on the sidewalk, depending on where you do it. Yes. Okay. Also, one other thing you might have noticed, some of you may not have noticed, is that as the objects got heavier, likely the static and kinetic friction values further apart. Yep, that's a distinct possibility as well. So part of the reason I wanted to point this out is sometimes we don't really think about the results we get in an experiment. And so we don't really get to that point where we say, oh, yep, when I increased the friction between the rug versus the countertop or the sidewalk versus the table or however you did it um, in your particular experiment. When we changed that, the static and kinetic frictions changed, and the static friction is pretty um, pretty significantly changed for some of us. But what should have happened, regardless of what surfaces you used, your static friction should have always been higher than your kinetic friction. Okay. And most of you seem to agree on that. All right. So we're going to watch a video here in just a moment. And our video is going to be about Galileo. So if you remember from your reading, awesome. If you don't, I put it up here. Remember that Galileo lived in the late 1500s and early part of the 1600s. Okay. He was a mathematician and a physicist, and he played a key role in unlocking some of these ideas that made the way for Newton to kind of set out the laws of motion. One of the things that we're going to look at here in just a moment is going to talk about how, Galileo really stretched scientific thinking because before he started some of these experiments, scientists tend to believe that if an object is in motion and we want to keep it in motion, that the force has to, some sort of outside force has to act on it. And Galileo said, no, it's actually the opposite. Once it's already in motion, you would have to put a force on it to cause it to stop. Okay. So that's where he came with this idea. So let me put our video up here as a way to kind of help understand some of this experimental stuff that he was doing. And then we'll actually talk about that along with Newton's ideas. So here we go. Okay, so just kind of a quick glance at this. This is a Galileo track, right? So this is something where what he was trying to show is that in the picture here, if you reduce friction as much as possible, then objects in motion are going to stay in motion. So it allows you to see how some of these ideas we're seeing situations where they don't seem to be true, but they actually are. Because while we don't always acknowledge it, in a lot of these situations, they are being acted upon by an outside force, and that force is friction. So if you remove that outside force, like Galileo was trying to do, if you could eliminate friction, then the ball will either come back to its original height or it would roll on forever and ever because there was no force causing it to stop. That idea began to help set the stage for Newton's discoveries and what he saw. So, do the things that you saw in Galileo's experiment make sense to you? Do you see how that kind of set the foundation? Good. Okay. All right. So then let's take it further and start to understand how Newton's ideas developed and kind of what they developed into. That's the part that's going to be the subject of what we're going to talk about next. So, when Newton got this first law of motion developed, okay, an object that is either in motion or at rest is going to continue doing what it's already doing until it's acted upon by an outside force. So, if the object is in motion, it's going to stay in motion. The object is at rest, it's going to stay at rest until an outside force causes it to change. That's what it means when it talks about the law of inertia. That's what we called inertia. And it talked about that just for a second in the video. That resistance to change. Basically, it wants to keep doing what it's already doing. So, part of the reason why Galileo needed to set that foundational understanding is because the ideas of Newton directly contradicted what Aristotle had said. So Aristotle said the natural state or the state that an object prefers to be in is at rest, and that force has to cause it to move, but that it's always trying to move back to being at rest. That's where Newton changed his a little bit. He said, no, it wants to keep doing what it's already doing. So that's where this idea of inertia came from. So because that word might be a little new, I kind of defined it on here for you. So it's the tendency or the property of an object to resist change in velocity. If it's not moving, it wants to stay not moving. If it's moving, it wants to stay moving. Okay. So in your reading, what characteristic, what property of an object determines how much inertia it has? You remember from your reading? Thinking back to what you read last week, can you remember what determines how much inertia an object has? Good. We're going to use a slightly different word. Good. So the word, we're going to change it just slightly and not just say the size of it. We're going to say the mass of an object. So the more mass that an object has, the more inertia that an object will have. So a lot of us were on the right size, on the right track, saying the right words with size and weight, but we're focusing in specifically on its mass. Okay. So if I gave you some super simple examples, which of these two has more inertia, a bowling ball or a tennis ball? Okay. So a lot of us get an easy understanding for what that is. And so if I give you something that has significantly different things, where it's easy for us to pick out. So same thing. What about a hammer versus a feather? Okay. So it doesn't have to roll for it to be inertia, right? Think about even if you were to move it yourself, what would be what would be more resistant to change, meaning have higher inertia. Good. Okay. Now, when we think through these, this first part is very easy, but not all of us think this way through the words. So I have a picture to help you remember. Okay. So if I'm looking at this car and now I'm putting some values that go along with it. So I want you to think for just a minute, but don't give your answer yet. Just think. My question in this picture is based on all of the forces that you see acting on this car, if right now it is moving forward, is it speeding up, slowing down, or maintaining the same motion? Remember, think about it for just a minute. See, this is why I have to pause chat because we already start typing. We aren't listening to say, Pause, hold on, think about it." Because one of the things that a lot of us see is words are hard, like when we only have words on the screen. So having pictures helps us kind of solidify it in our mind just a little bit more. All right, so feel free to answer when I look at this, is it speeding up or slowing down? If you feel that it's maintaining the same speed, you can say that as well. Okay. All right. So for this one, if right now it has 200 newtons force up, 200 newtons force down, those are balanced forces. Balanced forces don't cause motion. If it has 6,000 newtons force to the left and 8,000 newton force to the right, that's where I have an unbalanced force. That is how I know that it is slowing down. Okay. So as we look at these, the thing I want you to be able to see and identify is just saying, okay, if I see this unbalanced force, I know that motion is happening. And a very different kind of picture form here before we take our first pause. Think about this picture for just a moment. I want you to think about how this picture could be showing inertia. Don't tell me anything yet. Just think about it. All right. How is this picture showing us inertia? There you go, several of us. Good. So if I think about the picture for the truck, clearly an outside force acted on the truck to cause it to change its motion. So likely the people applied the brakes caused the truck to stop. However, there is no force directly acting on this very large rock that you see or stone. So even though the force applied to the brakes caused the truck to stop, that force is not directly applied to the big stone. Yep, that does not cause it to stop. So that ends up in a very problematic situation. Okay. A lot of times, something like this will happen when you're just not familiar with the things that you have to do to transport large objects. So it definitely makes sense to understand, oh, there are some things at play when you're transporting very large objects. So definitely some things there that will potentially be problematic. So it's important for you to kind of think through those and see, oh, this is actually back to high school or back to middle school or back to elementary school or wherever you might have read about these or seen these before. Okay, good. All right. So we're going to pause here and take our break. When we come back from break, we're going to talk more about Newton's laws. We're going to talk about our lab. Like I said earlier, we may or may not have time to complete the lab in class. It's more about just making sure that you understand the experiment so that you can complete it later. Okay. All right. So let's pause here and take our break, and I'll see you guys back here in just a few minutes. All right. So let's continue some of our conversation so that we have time to get to our lab and some other ideas here shortly. So when we're thinking about especially inertia, we want to think about what forces can cause motion to stop. We've talked a little bit about friction being one of those forces. Gravity can also be one of those forces. And then another example can be barriers, right? A wall, a pole, things like that can very frequently be problematic barriers to stop motion in a very bad way, right? We don't really want to stop motion that way. We would much rather have the friction of applying the brakes as opposed to having to find a barrier as our stopping way. Okay, I turned the camera off. I'll turn it back on in a moment to see if that helps. It looks like you have a little bit of lag from your end on your Wi-Fi, so not a ton we can do about that. Sorry. All right. So in a problem like this, you had a fun little example like this in your book, and it said, okay, as this eagle is flying, when he gets over the first person, he drops the taco. Who will catch the taco? Have you seen one like this before? Good, good. So to make it more fun, visual, interesting, here we go. Here's our little guy. He drops the taco, and even though he releases it, meaning the taco is no longer being carried forward, that inertia means it doesn't just stop the motion right away. It has to have those outside forces acting on it to begin to slow that motion down and eventually stop the motion. So the animated version of it here just makes it a little more interesting to see what's happening, but just helps you keep in mind when you have a giant eagle carrying a taco. Definitely it helps you keep in mind a weird thing you saw in physical science, but more importantly, it helps you keep in mind how that moment of inertia continues the movement of the taco even when he's not carrying it anymore. Well, he likes tacos just like everybody else, right? Why not? All right. Newton's next law is one that simply helps us understand mathematically how force, mass, and acceleration are related. So remember, we talked about force. We said force has to do with the push or pull on an object that causes change in its velocity. Okay. We said it had a super weird unit called a Newton, which is made up of kilograms, it's made up of meters, and it's made up of seconds squared or seconds times seconds. Okay. Also, if you remember, we talked about how force is a vector quantity, meaning we can't just give the value, we also need to give the direction of that value. So the way that we calculate force is that we take a mass of an object and we multiply that mass times its acceleration. So if I increase the mass of an object, then in order to increase its acceleration, I know I'm going to have more force. Okay. So it helps you kind of see how they're related. But this law from Newton is really focused on helping values, put in numbers, calculate expected values here. And then our third law of motion is the one that says every action has an equal and opposite reaction. So I have several examples here. There are even more given in your book. Everything from having an inflated balloon blown up but not tied off. When you release the end of the balloon, the air that's inside is rushing, trying to get out. That would count as our action. What would the reaction be? What would happen to that balloon? Yep. Up, down, all around, maybe, right? So the balloon is going to be carried in the opposite direction from where that air is trying to escape. Bye, Logan. Thanks for being here. Okay. In the same way, a rocket ship can blast off as it expels that fuel one direction. The reaction is going in the opposite direction to launch that rocket. Lots of examples: paddling a canoe, firing a bullet from a gun, even jumping out of a boat could all be examples of how when you have an initial action, the response, the reaction, goes in the opposite direction, but with the same amount of force. Okay, so let's transition here. We're going to talk a little bit about your lab, and then we've got some practice things we'll do in our group. Likely, what we're going to talk about is just what you're supposed to do in your lab. We're not going to pause and complete the lab right now. This one is really focused on trying to actually just talk about what to do in the lab. Okay. All right. So I'm going to put up the force mass acceleration lab document. It was the same one that was in the class page, the same one that was on the files for class here a few minutes ago. Okay, here it comes. So when I look at this, I said, okay, here's kind of what we're trying to do. I gave you an initial explanation for what was happening. Okay. And I gave you a question: how does the mass of an object affect its acceleration? So, some leading questions to help you form your hypothesis. I asked you a couple of specifics and then said, if the blank, which is the independent variable, is whatever happens to be happening, then the dependent variable will whatever. I put that on there to remind you that when we write a hypothesis, we say if something happens to the independent variable, then here's what we expect to happen in the dependent variable. So I was trying to remind you about some of those ideas. Okay, so then you've got your materials listed here. I want to go through the setup of the particular experiment and talk about what you're supposed to do. Even though all of the directions are here for you, I want to talk about it a little bit because some of us struggle with the setup if we haven't talked about it, and some of us struggle with the calculations. So if I can go through them first, you do much better with them. So when we are going to set up our experiment, okay, you're going to take the mass of each different type of ball that you're going to use first. Record them on the table. I'll show you the table here in a minute. Then you're going to take a piece of tape, put it on the floor. The ball is going to sit just in front of that piece of tape. That's going to be your starting line. Then you're going to have another piece of tape that is 5 centimeters behind the first tape. Okay. This one is going to be your launch. So from the front side of the start to the front side of the launch should be 5 centimeters, which I've denoted here for you. Okay. Then finally, you're going to measure 100 centimeters or 1 meter from the starting line and put down a third piece of tape that will be your finish line. Okay. Does the setup make sense to everyone? I tried to do not just the words of it, but also a picture to help you visualize it better in your lab write-up. Makes sense to everybody? Good. All right, so you're going to take one of your objects, whichever ball you choose to use first is fine. You're going to set it here at the starting line. Then it tells you you're going to take your ruler. You're going to pull back the ruler until it matches up. So essentially, you're going to start with it. Oops, I don't know why it went away. You're going to start with the ruler right here at the back of whatever ball you're using first. You're going to hold on to it with your hand right here. And with the other hand, you're going to pull that ruler back to the beginning of the launch line and let it go. So I was looking for my ruler that's here that my children frequently borrow. Who knows where that went? Okay, so it would essentially look like this. Let me move this for a moment. So if I line my ruler up with the ball, I'm going to hold on to one end, I'm going to pull it back and then let go of it and let it strike the ball. Okay. One of the things you guys have to be aware of is that you try to use about the same amount of force each time, meaning one time don't pull it back and let go really hard, and the next time super soft. Just try to keep it consistent. Okay. Then you're going to likely need a partner so that you can do that part and they can time how long it takes for whatever ball you're using to travel across the finish line. Okay. So I would allow you some flexibility on that, but I would encourage you to you be the person who's actually launching the ball and let your partner be the one that when the ball strikes, or I'm sorry, when the ruler strikes the ball, starts the stopwatch, and when the ball crosses the finish line, stops it, and then you record that value. Okay. And you're going to do that same process for all 3 of the different types that you have for the ping pong ball, the golf ball, and either a billiard ball or a baseball. Doesn't really matter which one you do. Okay. Once you have done all of that, you'll need to do the calculation table. Okay. So the one that you have here is your mass. You recorded that first. I told you just to put that down in the table. But what you're going to need to do here is to record your information and use it. Here it is. Record your time here and use it to do your calculations on the next page. It asks you to calculate an initial velocity. What will your initial velocity be for the different balls in this experiment? What is their starting initial velocity? Anybody have a thought about that one? Right. At the beginning, it's not moving at all. So your initial velocity for all of these is going to be 0. Okay. Then you're going to use the directions that are down here below to help you calculate the other things. Okay. And I gave you directions on this page, and again, more directions on the last page to help you do all the calculations. Even though these same directions are in your book, I tried to make it more helpful for you and put the directions also on the part here just to make that easier for you to do. And then at the end, it wants you to graph the results, okay, with mass and acceleration for each of the balls, okay. Remember that the very first thing I asked you on this was to identify the independent and dependent variable. So that helps you know independent is going to go on my X, dependent is going to go on my Y. It helps me go think through some of that. Okay. Also, be careful and think about what kind of graph you use. A lot of you do a really good job with this, but some of us use graphs that don't make sense. Like you'll be doing something like this and you'll use a pie graph or a circle graph, which doesn't really make sense. So make sure you think about it. If when you're doing this, you're struggling, you have a question, you need help, feel free to reach out. I'm happy to give you better explanation if you're struggling with that. Okay. All right. I just wanted to talk through everything you need to understand for the lab. You are not going to complete this one with me here in class. I just wanted you to know what all you need to do. A lot of you will take advantage of the time right after class if you have time and go ahead and complete the lab there. That's great. If you need to do it later, that's fine too. Doesn't matter to me either way. Are there any questions before we start talking a bit about some practice problems over the ideas we've been learning? Okay. Okay. All right. I'm not seeing questions show up. Everybody seems to have a good idea for what we're doing. So let's jump back here. Let's look at a couple of practice problems. We're going to try some of them together, and then we're going to start doing some practice and discussion with with a small group here in just a moment. So take just a minute. It says a 100-kilogram bag of sand has a 100 Newton force acting on it. What would its acceleration be? So if we think back to our guess method that we learned about last unit, remember what do we start with what we're given? What are we given in this problem? Okay, what is that? You're right. What is that? So if you see that 100 kilograms, that's a mass. We're also given a force of 100 newtons. So this is where I'm forcing you guys to really pay attention, because a lot of us rush to say, here's the answer, done. That's great. In simple problems, that works out fantastic. But for a lot of you, when you get into the more complex problems, you're the type of student that struggles because you haven't taken the time to learn the process. You've spent your entire time trying to find an answer. That's not a question I'm ever going to ask on a test. I'm not going to copy the question we have now onto the test. You're going to have to use that information and those skills on the test, which is why I never focus on how quickly I can give you the answer, just making sure that you know how to find it. Okay, so the two things that we're given are the mass and the force. What are we trying to find? Exactly. Trying to find the acceleration. What is our equation that we're going to use for this? What equation do we know that involves these? Good. So our equation that we learned just a few minutes ago said force is equal to mass times acceleration. Try to move this where it's easier to see. Okay. So when I plug my values in, I would say 100 newtons is equal to 100 kilograms times the acceleration, which is what I'm trying to find. Remember that newtons is made up of kilograms, meters per second squared. So that will help me determine what answer I will have here in a minute when I deal with those. Okay. Since right now the acceleration is being multiplied by the force, I'm sorry, by the mass, if I want to undo that, I would divide each side. So 100 is being multiplied, so I'm going to divide each side. But watch, if my newtons are kilogram meters divided by seconds squared, and I divide it by kilograms in my mass, then my unit for my answer is going to be meters over second squared. So my answer is going to be acceleration is equal to 100 divided by 100, 1 meter per second squared. Take a minute, look at that one. Does that one make sense for you? Good. Okay. All right, for our second one, I'm going to go through and do the guess as well. I'm not going to just jump to the answer. I'm going to go through and look at the guess for this one as well. If you already have the answer, that's fine. I'm just going to type in all of the info first before I give you the answer. So for this one, our given is a mass of 1,600 kilograms and an acceleration of 4.5 meters per second squared. The thing it's asking me to find is force. My equation is going to be the same one we used just a minute ago. Force is equal to mass times acceleration. So when I substitute it in, it would say 1600 times 4.5. So here is all of the info that we've got so far. Does all of that make sense to you? Okay. And I came out with a force of 7,200 newtons. How do we do on this one? Good. I took off the other S. I just put the final answer for that one. That's the equation. Correct. Okay, do you feel like you understand all of the parts of these types of problems? Okay, so I want you to take just a moment. What you see in this picture, so we did several practice problems on Newton's second law, force, mass, acceleration. I want you to take just a minute, look at this picture. There's 3 different examples in this one picture. If I asked you on a test, on a practice problem, on a homework, to use an arrow to label the reaction, think what that would look like for just a moment, and then I'll ask you to describe it for me. Okay, so if I look at the first picture, you see a young man lifting up a weight, right? So as his force is pushing up on the bar, that's the action. What would the reaction be? Okay. So hopefully they're not going to fall, right? But the reaction is going to be gravity pulling down on those weights, which is what's causing this bar to bend. Yep, very good. Okay, in the second picture, you've got a bowling ball headed towards a bowling pin. When the bowling ball strikes the pin, that's the action. What would a reaction be? What would our reaction be on this one? Several of us typing, but no one's actually said, what would our reaction be on this one? Okay. So not just slows it down, it actually causes the ball to move backwards in the opposite direction when it comes into contact with it. Good. Yep. There you go. So the pin falling will be still part of the action because that's all moving in the same direction. Remember, our reaction force has to go in the opposite direction. It helps you kind of see how that process works. And then finally, if we've inflated a balloon, the action is that whatever air we've used to inflate it, whether it's air from our lungs or helium, that air pushing out against the balloon to hold it open. That's the action. What would the reaction be? Think about it. What would that reaction be? It's our last thing before we finish. Good. That's exactly right. The air on the outside pushing back against that balloon as well, right? So this opposite direction. Exactly. All right. So this week, you're going to complete the lab and fill out the lab report about your force, mass, and acceleration experiment. And you're also going to complete the Module 7 study guide. So thank you guys for being here. Have a fantastic week. Stay warm, and I'll see you again next Wednesday. Thanks for being here, everybody. See you next time.